Okay, let's dive right into this. Welcome to today's Explainer, where we're going to completely demystify one of the most powerful and, honestly, most misunderstood machines on the planet, the nuclear reactor. We're going to build one together, conceptually speaking, starting from the absolute tiniest atomic level and working our way all the way up to those massive power plants providing electricity to literally millions of people. I mean, it's the ultimate question, right? When we hear about nuclear power, it almost sounds like straight-up magic. But today we're stripping away all that mystery. We're going to reframe the nuclear reactor, not as some incomprehensible sci-fi device, but as a surprisingly elegant, highly advanced thermal engine. Because at its core, it's really just a thermodynamic system, kind of like an old-school steam engine. But instead of burning coal or gas, it's driven entirely by the fundamental physics of the universe. So, here's our roadmap for this explainer. Number 1, the invisible spark. Number 2, building the engine. And number 3, the two big designs. Let's get into it. Section 1. The invisible spark. To really wrap our heads around those towering cooling towers and massive turbines of a power plant, we actually have to start at a scale so incredibly small, it's completely invisible to the naked eye. We've got to look at our heat source. And that heat source is a process called nuclear fission. In a standard reactor, uranium nuclei, specifically the isotope uranium-235, are bombarded by neutrons. When a single neutron strikes a U-235 nucleus, it forces that atom to split right into two smaller fragments. This one single microscopic event releases an absolutely extraordinary amount of energy in the form of heat, alongside 2 or 3 brand new, high-energy, super fast-moving neutrons. Now, what's really interesting about this slide is how we get from a single atomic split to a sustained chain reaction. See, when that uranium splits and releases those fast neutrons, those new neutrons are actually moving way too fast to effectively split another uranium atom. They literally need to be slowed down. And this is where a material called a moderator steps in. Through a series of elastic collisions with the moderator's molecules, those fast neutrons lose momentum until they reach a state of thermal equilibrium. We call these slowed down particles thermal neutrons. At this much slower speed, they can efficiently strike other uranium nuclei, causing them to split, which releases more heat, more fast neutrons, and boom, the cycle continues perfectly. Section 2. Building the engine. Now that we've got a handle on that invisible spark, the sustained chain reaction of fission, we need a way to actually harness it. So it's time to physically build the machine that houses, protects, and controls all this immense atomic energy. Just take a look at the sheer, massive scale of a modern nuclear facility in this cutaway. It's a total marvel of engineering, isn't it? To make sense of all these pipes, pressure vessels, and containment structures, we're going to build out the core components using a super simple analogy. I want you to think of the reactor as an engine, with a gas pedal, a set of brakes, and a seriously heavy-duty cooling system. Okay, so we start with the gas pedal, which is our fuel. Natural uranium is mostly uranium-238, which doesn't split all that easily. So it's enriched to contain about 3 to 5% of that highly reactive uranium-235 we talked about. This enriched uranium is processed into these little ceramic pellets. Then, they take those pellets and stack them end to end inside really strong sealed metal tubes to create what we call fuel rods. Because a reactor needs a massive amount of fuel, they bundle more than 200 of these rods together into a fuel assembly. Finally, depending on how much power the plant generates, a reactor core is typically made up of a couple hundred of these assemblies packed closely together. But, just piling up fuel rods isn't going to cut it. Remember those fast neutrons from earlier? If they just go flying out of the fuel rods, they won't trigger any more fission. They need that moderator. In most commercial reactors here in the US, normal liquid water acts as this moderator, though in other designs globally, like the CANDU or AGR reactors, they might use heavy water or graphite. The moderator sits right there amongst the fuel rods, acting as the crucial medium that slows down the fast neutrons so our chain reaction can actually thrive.
So the crucial point is, once this reaction gets going, how do we stop it from just growing exponentially? Well, we need our brakes, and these are the control rods. Control rods are made of elements like boron, cadmium, or silver, basically materials that are unbelievably good at absorbing neutrons without becoming dangerously unstable themselves. When operators want to decrease power or just shut the reactor down entirely, they drop the control rods deeper into the core amongst the fuel assemblies. The rods just swallow up those free neutrons, starving the chain reaction. Want to increase power? They slowly raise the rods back up. And in an emergency, these rods can be dropped all the way in by gravity to instantly kill the reaction, a fail-safe process known in the industry as scramming.
All right, so we have our fuel generating heat, and our control rods regulating it. And let me tell you, the heat we're talking about is absolutely staggering. Inside a typical pressurized water reactor, the primary coolant surrounding the core reaches temperatures of around 330 degrees Celsius. That is over 625 degrees Fahrenheit.
Now you might be wondering, wait a second, how on earth can water be 330 degrees Celsius and still be liquid? Doesn't water boil at 100 degrees? Well, that's where pressure comes into play. The reactor vessel is pressurized to an immense 16 megapascals. To put that into perspective, that's over 150 times normal atmospheric pressure. This extreme, crushing pressure physically prevents that superheated water from turning into steam while it's inside the core.
So this incredibly hot, highly pressurized water acts as our engine's coolant. Its main job is to constantly flow over those intensely hot fuel rods, extract their thermal energy, and safely transport that heat away from the nuclear core. Water is just fantastic for this because of its high heat capacity. It carries the heat away to be used in a thermodynamic process, the Rankine cycle, where that thermal energy will finally be converted into mechanical work to spin a turbine. Section 3. The two big designs. Let's zoom out to the macro level and see how this all builds together. We're going to look at exactly how different plants turn that hot water into steam. While all commercial reactors in the US use normal light water as both their coolant and moderator, they differ in exactly how they use that hot water to make steam. There are two dominant designs we really need to look at.
Over on the left, we have the pressurized water reactor, or PWR, which actually makes up over 65% of the US fleet. Like we just discussed, the PWR keeps its core water under such high pressure that it never boils. Instead, it pumps this super hot liquid to a totally separate piece of equipment called a heat exchanger. Here, it heats up a completely separate lower pressure loop of water, turning that second loop into steam, so it's an indirect steam cycle. Now on the right, we have the boiling water reactor, or BWR. This design is a bit more direct. The water is heated by the fission in the core and is allowed to boil and turn into steam directly inside the reactor vessel itself. That steam is then piped straight to the turbines. Interestingly, because the BWR produces steam right at the very top of the reactor vessel, it actually requires steam drying equipment up there. And because of that, BWRs have to insert the control rods from the bottom of the reactor using hydraulic pressure, whereas PWRs just drop them in from the top using electromagnets.
And this brilliantly illustrates the elegant harmony of the entire system. Think about it. From a single neutron splitting a single atom, we harness that intense heat. We carefully balance the reaction using precisely engineered fuel assemblies, moderators, and control rods. We use high-pressure coolants to transport that heat, generating steam either directly or indirectly. And finally, that steam spins massive turbines to generate the reliable, secure electricity that powers our modern world. It is, without a doubt, a stunning achievement of physics and engineering working perfectly in sync.
But the engineering doesn't just stop here. While traditional reactors are absolutely massive, generating well over 1,200 megawatts, there's a huge growing interest in the next evolution, small modular units, generating as little as 10 megawatts. Just imagine this exact same incredible physics, shrunken down, made even safer and highly modular, capable of powering remote communities or industrial sites entirely without carbon emissions. The atomic engine is continually evolving, and understanding its core principles is really the key to grasping the whole future of energy. Thank you so much for joining me on this explainer today, and keep learning.